what we're going to discuss today is a totally different subject, and well, let's start with something. Well, I would say simple, okay, but you would see that the real problem with this definition that we are going to examine right now is not a geometric problem. It's just how to translate the geometric needs we have into some working script in Grasshopper, because it needs some. I wouldn't say some heavy data manipulation, but well, it's not like that intuitive. Okay, so what we want to do is basically something. Well, I would say quite stupid, but I want to take a couple of points, like for example these 2 points here, and what I want to do to create during the simulation is that these points are attracted to each other, and they stop when they reach a given distance. Okay, so I want to have a controlled separation between these two, a controlled distance between these 2 points. Okay, so this is something that it's very easy, right? So we have 2 points here. We want to connect them together. The easiest way to do this is to get a polyline in order to have this single line segment here. So I would say it's quite stupid, because we already know that if we take, for example, a length line and we convert this line into a spring, and we say that the rest length of this line must be a specific value. For example, I don't know, 2.00. Okay. So if I do this and I use, for example, Kangaroo solver, creating this spring here, you see that these points already are at the given distance. So this is a very easy simulation, right? And we can also double check that the result is good, because we have the two particles, the only two particles involved are here. So I can also create another polyline with these two particles, get rid of the view of the initial status of the system, and eventually analyze this length and see if we got exactly the same value. And you see that exactly we have 2.0, right? So if I increase this value, I also see that it corresponds to the given length that I want to reach during the simulation, okay? So it's pretty obvious when you work with a couple points, okay? But what happens when we start increasing the number of points? So I'm going to stop this simulation in order to don't have it running. Okay, so that's it. And what I want to obtain is the same behavior, but with 3 points, like this. So we have these 3 points here. Now, the problem is that if we work with this configuration, you see that the final polyline only comes out from 2 points. Why is this happening? Why don't we have the other segments? Well, first of all, because if we draw a polyline starting from 3 points, this is the result that we get. And this is because the polyline is naturally not closed. So if we want to consider 3 different attractions between these 3 points, we must invert the closed parameter in order to have this closed polyline. But the real problem is that the length line accepts lines. And if we pass a polyline, which is a curve, actually you see that the line component asks for curves. You see the black hexagon icon. This is the parameter for curve. But Kangaroo works, as you might know also from my previous webinars, that Kangaroo only works with ideal springs. So ideal springs, remember, that are linear elements, right? They can only work in this longitudinal direction. They can basically stretch, like expand and compress, but they cannot bend. So they must be lines, okay, even if this says curves. So I strongly suggest that you always convert each curve that you want to use as elastic shape. You must convert it into line segments. So the only thing that we miss here is eventually a explode curve. So now we have 3 line segments. that we can pass to the length line component. Okay, so this is the normal approach that you might want to adopt. So if I reset the simulation, you see that now we have the 3 connections available. So these are 3 springs. And if we run the simulation, you see that here the polyline, well, actually is no longer representative of our problem because we have 3 segments and not just 1. Okay, and so if we draw the polyline, even if it is not closed, what we are getting is twice this distance because it is calculating the length of 2 segments connecting 3 points. If we close this polyline, we get 3 times this value because we are considering 3 segments with the same length, right? So everything works fine, but with 3 points, because the problem is that we are building a polyline, okay? But we can also create another structure, which is simplified by Kangaroo, which is this one, interconnect points. So if I interconnect these points, what I get is 3 segments that I can measure here with this length, and we have exactly the same length for the 3 segments. And this is also verified if I change the desired rest length. Okay, so we can still solve the problem when we have 3 points. Now the real problem happens when we have 4 points or more. Okay, so I'm going to reset the simulation, and I'm going to select like multiple points, 1, 2, 3, and 4, and reset the simulation. So our system actually is this one, and we can no longer work with the polyline because the polyline is just creating 4 connections along the, well, outer perimeter, right? So if I get rid of the interconnect points, you see this is the polyline that we are considering. But if we want to consider the mutual attraction between these 4 points, we cannot only consider this connection here. We must also consider the diagonal connection because these points will also be attracted by their, well, not so neighbors. Okay, so even in this case, we cannot use polyline and explode. It's better to use another interconnect point, right? Because if I do this, I get all the connections possible between this set of points. Okay? And this is already giving us line segments. So I can get rid of this construction and just use the interconnect points in order to do this. Okay. So we have prepared the system. We can reset the system. This is actually the final result. Now, if I run the simulation, I start to get this thing here. Okay. This thing is not that it's not working. If well, actually, with the interconnections, we start to get some weird result. You see that we have either 6.5 or 9.2, which has nothing to do with this value here. Okay. The real thing is that when we get these particles, which are the 4 points, basically, we can also create, for example, a circle starting from these things here and having this radius. Okay. If we use this radius, you see that this circle is not even close to represent the new distribution of these vertices. Okay. Eventually, I would expect, for example, one of these, well, these circles to start from one center and reach the other point. But this is not possible because this algorithm here, considering just the distance between, well, the springs between this object, is not considering, for example, collisions or something like avoiding these points to get too close to each other. And also we have 2 different sets of connections, which are basically the neighbors connection and also the connections with points that are not close to our initial point. This becomes more and more evident if we try to work with more points. So for example, if I try to use a not POOP, sorry, a populate 2D, well, in this case, I would expand the region and also decrease the amount of points in order to start working, because else we get too much connection and everything becomes so chaotic. But if I do this, you see that this is the initial configuration. Okay, so now it's a little more evident that there are connections that are well, somehow more complex to be taken into account, because this point here is being connected to all the remaining points of this point cloud, right? Also with this one. So if we say that each of these connections must become a spring with a constant rest length, it's evident that Kangaroo cannot basically pack these points in the plane, considering that there are closest points and farthest points. Okay, so we want Kangaroo to pack these points in the plane, considering that the mutual distance must be constant. Okay, so let's see how we can do this. And this is something that, for example, this is the first situation in which we better go back to Kangaroo 099. So today we are going to work with 099 because it is easier with 099 to program this behavior that we want to achieve. Okay. Later, if you want, you can do it like as your own exercise. After having created this script with Kangaroo 099, I invite you to try to do the same with Kangaroo 2. Because Kangaroo 2 lacks the necessary components, the necessary goal that we are going to use. And so you must find a workaround to program the same behavior. But I already did it, of course. But what happens is that the behavior that you get from Kangaroo 2 is simply creates a unstable system. So it's very difficult to find the balance between all the strengths of the different codes that you are going to use in order to program the same behavior. So this is the problem that we want to solve. And what we are going to do, we are going to solve it with Kangaroo 099. So I'm going to switch to 099. Okay. And let's start from scratch. So we have a clean definition here. So I'm going to use a populate 2D, as I told you, with less points and with a, well, I don't know if a wider region is so relevant. I'm going to stick with this one for now. So we have this population of points, right? Now, what I want to achieve is that the mutual distance between this point is given by one single value, okay, like 2. So first of all, we must use interconnections because this distance must affect all the possible connections between these points if I want to have this mutual distance, okay? So what I would do in this case will be eventually use the, well, you see that some components are basically still present in Kangaroo 2, but they were already present in Kangaroo 099, like the connect points. Okay, actually, this is something that it's not so good when you have both Kangaroo 099 and Kangaroo 2 installed, because when you type, for example, interconnect points, you see that there are two options, right? One is from Kangaroo 099 and one is for Kangaroo 2, but you cannot simply distinguish them because they are identical also in the description. Now, this can be a problem because there are some tools in Kangaroo 099 and Kangaroo 2 that simply because of the change of version don't work properly. So when you work with Kangaroo, try not to type commands here in the command line or in the canvas, because you might run into this kind of error. Okay, so this is a common mistake that normally happens when you start working with Kangaroo and you have both versions installed. So avoid this. So just grab the component from the corresponding toolbar, and now just create the interconnections between these points. The only problem with these definitions that we are going to create today is that if you have, for example, 11 points, you get a huge amount of interconnection, like 55. So when you work, for example, with the standard population here, which is 100 points, you start getting 4,950 connections. So the scripts that we are going to create sometimes might become heavy, but this is as we are only working with actually with lines, points, circles, and that's why we are going to use simple geometries today, like circles, spheres. Okay, if you work with this simple geometry, things are still under control. So Kangaroo can calculate its stuff like quickly, and then you get also almost a real-time response in the viewport. Okay, but as I told you, let's start with a few points and therefore few connections. Okay, so what we want to do with this with these springs? Well, first of all, the way that we create springs in Kangaroo 099 is not by simply defining the rest length, which is the method that you use in Kangaroo 2. Remember that with Kangaroo 2, this is the spring. So it only asks for what is the connection line, what is the rest length that you want for this line, and what is the strength that this line adopts when it wants to shrink or expand to this rest length. Okay, so it's very simple. While in Kangaroo 099, you have a totally different component, which is springs from line. Okay? Now, springs from line has some interesting behavior, and actually, this is a more complete physical simulation for springs. Okay? For example, springs from line allow, for example, programming some complex behavior in terms of physical behavior, which is connection is basically the line. You always see that here you have this black hexagonal icon, which is the curve parameter. But always remember that you see the description is line connecting 2 points. Okay, so if you try to pass a polyline or a NURBS curve to connection, this component will simply crash or become red. Okay, so it's an error. So always try to work with the single segments line. Then there is stiffness. Now, stiffness can be basically associated to the strength. Okay, so it's very easy. Then there is damping. What is damping? Damping is what happens when for example, let's say that you have a spring like this. Sorry, I'm drawing with a mouse, so be gentle. So if I have this spring and I apply a load to this point here at the end, and I anchor this spring to the top, right? If I apply a load, this spring here is going to extend, right? And you know there is a balance between the elastic force and the action that I am producing here, that I'm applying, which basically it establish a relationship between the strength of this load and the deformation that we get inside the spring. Okay, remember that we are talking about ideal springs, so they can only expand or contract. Now, what happens when I release the load? So I eliminate the load from this system. The spring tends to go back to its rest length, right? So its rest length is still here. So let's say that this was its rest length, and we got this delta length here. So if I stop applying a load, the spring goes back to its original rest length, but the spring is an elastic body. Okay, so what happens is that this spring tends to go back to here, but passes the rest length point, and then goes back here, extends a little, contract a little, extends a little, contract, extends, and so on. So it starts to bounce around the equilibrium states. Okay, so this is defined by the damping. So this bouncing here means how much bumping phase you have while the springs is looking for its equilibrium. Okay, and then there are these two values here, which are very important inside a Kangaroo simulation. Not actually, they are not exactly like physical behaviors, because it's like an abstraction. But upper cutoff and lower cutoff means if, for example, you have this spring starts from 0 and reaches a length of, let's say, 5. Okay, so this is the rest length of our spring. Now, upper cutoff and lower cutoff means, do you want the spring to stop working at these given distances? So upper cutoff means that, let's say that we give the upper cutoff identical to the rest length, which is something that we are going to do actually. We are going to use the rest length and the same value for upper cutoff. What does it mean? It means that this spring will only work when its length is smaller than the given upper cutoff. So let's say that I apply a load to this spring, which tends to expand the spring itself, and I get this delta length. So the actual length will be 5 plus delta L, right? So if I have this, it means that the spring will stop working. So there will be no action, no force from this spring from line, because the actual length will be higher than the given upper cutoff. And the same is for lower cutoff. If I set, for example, this spring to work only with a length which is higher than this value, then the spring will stop working if we compress this and reach a length or a work length which is smaller than the actual lower cutoff. Okay, so these are something like abstract parameter that we will be using today. So we are going to see them in action, so we will really understand how they work. But they are very useful inside a Kangaroo definition. And then there is plasticity, which takes into account that, you know, that Kangaroo, working with ideal springs, only considers or tends to consider only the elastic phase of the elastoplastic problem. So you know that when you increase, for example, the load, while the load increases, the deformation also increases, right? Like this is deformation, okay? But you reach a specific load in which the system still has some elastic phase, okay? But then suddenly you reach the break point, and this system starts to behave plastically. So that if you reduce the load, there is some deformation that is no longer recovered by the system. This is called the plastic phase, right? While we work normally inside this region here, which is exactly the elastic phase, which is somehow which keeps the system like in its ideal configuration, because if you eliminate the load, you also eliminate deformation. There is a plastic behavior that eventually must be taken into account. So this plasticity allows to create some plastic deformation in the springs. So some deformation that is not recovered by the spring if you stop applying a load. So as you can see, this component here is way much detailed than the actual Kangaroo 2 spring definition, okay? Of course, as I was saying, if you go into Kangaroo 2, you have the length line, but there is also the plastic length, you know? So there are always ways to reproduce this kind of behavior. It's somehow, I always say that somehow Kangaroo 2, as it has become a mass plugin, because it is distributed together with Grasshopper and Rhino, it has been somehow simplified so that users can more easily achieve the first results. But if you want to tweak something or obtain something more complex, then sometimes it's better to go back to Kangaroo 099. Okay, so today we are going to use this. I will leave this as a scheme, even if this is somehow unreadable, but I will leave it like here. And what we're going to do, we are going to use the Kangaroo 099 springs from line component. So basically what we want to do is use all these lines like connection lines. And what I want to do is use this radius here as rest length. Okay. So let's see what happens, because actually what we are doing is just substitute Kangaroo 2 component. You see, we have the radius, we have the interconnect points. We are just switching to Kangaroo 099, but we are doing nothing actually. So we only have substituted length line with springs from line. Let's say prepare the solver in Kangaroo 099. Remember that Kangaroo 099 solver, which is called Kangaroo Physics, accept force objects as list. Okay. Many people just flatten the input. Okay. I do prefer to do something different. I do prefer to use a merge component and flatten the result. So why this? Because here I have the possibility to just plug and unplug cables or wires inside this dynamic merge component. Okay. So if I plug or unplug cables, I will always get the correspondent list of forces applied inside the Kangaroo Physics. There are a few differences between Kangaroo Physics solver and Kangaroo 2 solver. The main one is the anchor points. So anchor points, you must specify anchor points directly connecting the points inside this input. Okay, so there is no actual anchor point in Kangaroo 099. You simply connect the points here. And you know, in Kangaroo 2, they have become a specific goal. And then there is geometry. Remember that in Kangaroo 2, you have the show component. Well, in this case, you simply connect the geometry you want to see after the simulation inside this input here. And as the output, you will have particles out, which are the particles. We already discussed this yesterday, which are the vertices of your geometry in the system that you are creating. In this case, they will be the endpoint of our interconnections. And then you have geometry out, which is simply the deformed version of the geometry input. Okay, so it's somehow more linear behavior in this Kangaroo physics component. So we only have springs. So I plug springs here. If you want to run the simulation in Kangaroo 099, there is a simulation reset which is set to true, which basically always switch back this Kangaroo physics to the original configuration. You can run Kangaroo simulation in two different ways. You can release the simulation by setting this to false and eventually connect a timer to this thing, or you can simply double click on the icon and this control appear, where you can reset the simulation, pause the simulation, and run the simulation. Okay, so if I play the simulation right now, this is what I get. Now, what I want to see is actually just the result. Okay, so I'm going to get rid of everything here and apply once again, just working with the particles because we have no other geometry in our original system. Just working with the particles, I get these interconnections. Okay, now you see that this is pretty interesting, but is not the solution because we have no constant separation between these points. So even in this case, as we are replicating what we already did with Kangaroo 2, we have the same result. So there is no particular meaning in this design unless you want to consider the nice pattern that comes out from the interconnections. So you have this kind of I don't know, mandalas situation here happening, which is somehow interesting by itself, but it's not what we want to achieve. Okay. So how do we deal with this? Well, we can do something like start using, for example, the upper and lower cutoff. So what if I want these springs to work only inside a given range of distances? So upper cutoff says spring will only work below this distance. Okay, actually set to 0, as well as the lower cutoff. So it means that this spring will always tend to reach this rest length. So it means that if you have this spring which has this rest length here, if you apply a load like this or a force like this, and this spring stretches like this, it will tend to go back to this rest length. If you apply a force like this will compress, but it will also tend to go back to its original rest length. If we apply a upper cutoff, the spring will work only below the rest length. So if I expand this spring, there will be no elastic force tending to compress the spring back to its rest length. Okay, so let's try to play with this one. If I plug this to the upper cutoff, so I want the spring to only work if they are basically compressed. So if I do this, you see that nothing changes. Okay, why working with upper cutoff should be interesting for us? Because if I get some spring to be shorter than this value here, I don't want them to act because it means that the points are getting too close to each other. Okay, so I cannot consider values that are smaller than this rest length. So upper cutoff could be interesting, but the problem is that if the points are too far, simply the springs are not working with these distances. Okay, so let me disconnect this and stop the simulation. You see that the distance between these points can reach values up to, let's say, this point. From this point, we have more or less 20 something. Okay, so let's grab a slider like 1100 and use this as upper cutoff. So we are considering a distance like half the width of our rectangle. Okay, so if I run the simulation, there will be some springs that will start to act. Okay, they will start pulling points together. While pulling points together, their mutual distance will be lower, and then the rest of the springs will be able to work. But you see that we always get some nice mandalas here, but this is not the point. Okay, so it's interesting, but we are not getting to the desired result. Okay, so what if we work with lower cutoff, for example? If I work with lower cutoff and I run the simulation, I get exactly the same behavior, okay? But these springs are only working when their actual length is higher than this value, which means that these springs only tend to contract and not to expand. So what happens is that if we consider a rest length of 2, there will be some points that will stay more or less a 2 millimeters distance, but when the points get too close together, the springs are no longer working. Okay, so we must find a way to make this point, let's say, get closer during the simulation, but also we want some force to maintain their mutual distance to the given value that we want to use. So the easiest way to do this is to use another goal which is present in Kangaroo 099 and is no longer present in Kangaroo 2. You see that Kangaroo 099 has all its forces grouped inside one single list here. And what we're going to use now is called the power law. So the power law is something like a, gravity, but real gravity, not gravity like G gravity. So it's mutual attraction. Okay. So what we can do with this power law? Well, power law works with lines, connection lines. We already have them. Okay. Then it says exponent. So exponent is basically multiplies the distance to get the intensity of the attraction. This is something that happens with gravity in space, right? So you have, for example, the Earth and the Moon. They are working with this kind of interaction. Okay. And then there is strength. Now, strength says if you set this value to negative, the bodies will be attracted to each other. If you set this to positive, the bodies will be basically, there will be some repulsion action. Okay? We can work with this system in two different ways. Either we set a repulsion action with the power law, and then we set the springs to work like to get our point together, or we set the power law like an attraction law, and we set the springs like to work to expand the point. It might look somehow like counterintuitive for us, but let's work with an attraction law. Okay, you can easily try and see what happens if you invert this situation here. But I will stop the simulation from running. You see, this is very nice to have this kind of control because you can simply place it where you want, and at any time, without going and looking for the Kangaroo physics component, you can simply rerun the simulation like from here. So what I'm going to do, I'm going to use the power law, like, let's try avoiding too much cable crossing here. So the connections will be the interconnections. I can also double click on the wire and create a relay, and then copy this relay and use it for connection. So this is something that I normally do to avoid intersections between wires in Grasshopper. This becomes very tricky when you have the spaghetti effect. So the strength of this power law is going to be a negative strength. Okay, so I'm going to use a negative just to have a direct control over the intensity of my strength, and I want this strength to be something like, I don't know, 5.00. So it's going to be minus 5.00 actually. So this is going to attract points together. And I want to use this as an additional goal. So I'm going to plug something like this. Okay, so what happens now? What happens is that I have this power law tending to attract each point to the other points. So if I, for example, leave the system like this and run it, you see that the power law is simply attracting points together, and I have the same springs as before that simply tends to get to this rest length. Okay, this is happening because these springs always work. There is no upper cutoff, no lower cutoff. What I want to program right now is the upper cutoff, because I want these springs only to work when their rest length or their length is actually smaller than this value here. So if I don't do this, if I don't limit the action with the upper cutoff, for example, what happens is that this action here tends to basically collapse this point structure inside one single point. So if I, for example, stop the simulation and get rid of the springs and run the simulation, you see that this is what happens. The point just collapses inside one single point. Okay. The fact that I am using these springs here makes the distance between these points basically stop when they reach this value here. What happens if I start using the upper cutoff? Okay, so if I stop the simulation and I say, no, I want the spring to work only when they are shorter than this length here, and not when they are larger than this length. So in this moment here, the springs are not working. The only thing that will work will be the power law. Okay, so if I run the simulation, I start getting this thing here. Now, take a look at the structure that we have. Don't pay attention to the large connection. Okay, just pay attention to the short connection. So let me grab a pencil here. Remember that these are the vertices. Okay, so look at how these vertices are packed in the plane. Okay, you see that these are creating these triangles, which are equilateral triangles. So it means that these lengths here are all identical. Okay, that's because the springs only works when they get shorter. And when they get shorter, they want to go back to this actual rest length. When they are larger, they have no action. So if you have this spring here, okay, this spring here is not working at the moment. So that's why you don't see the mandala effect in this case. Okay, so as the springs only work below the rest length value, what they do is just expand in case the points get too close together. This avoids the point to basically collapse inside one single position. Okay, so as you can see, this is exactly the effect that we wanted to achieve, because despite having here our interconnection lines, which are not so relevant in this moment, because I want to see all this mess of interconnection after the simulation. Okay, this is good for creating the springs and the mutual attraction. Okay, but I don't want to see this after the simulation. What I want to see eventually is some circles starting from the particles, okay, and having exactly this radius here. Okay, if I use this radius, what I'm programming here is that the mutual distance between the point is exactly identical to this value. So what I get here is one circle that starts from one point and passes through the neighbors. Okay, this is something, I don't remember exactly the name of this figure here, but it's something like, has to do with something like life, or I don't remember, something like in spiritual industry is very well known, but I'm not exactly a spiritual guy. But the tricky part here is that if we want to pack these circles, we just have to multiply this distance by 2. So if I stop the simulation and use, for example, this multiplication result, and I rerun the simulation, there is, oh yeah, sure, stupid me. Flower of life, thank you, Hitesh. I obviously I made a mistake here. If I double the this separation here, I must use the initial value as the radius. So you see that now we are exactly packing these circles in this area. Okay, and of course this is dynamic. I mean, the change in this value here doesn't affect the amount of geometry of our system. So remember that Kangaroo doesn't like editing the geometrical aspect of your system. So for example, the amount of points, we cannot change it dynamically because Kangaroo will simply say, okay, what do you want, right? So we must stop the simulation in that case. But this value is not affecting the geometric aspect of the system. It's affecting the intensity of our strengths, okay? So we can work with this dynamically and simply, for example, increase or decrease the radius for our circle. And you see that they start bouncing around if we make some sudden change because of the power law attraction. Okay, so this way you can easily fill a region of in our plane. So it's a two-dimensional region in this case with circles. We can customize, for example, the rectangle here, and we can start working with several more points. As there are some points that are at a mutual distance which is lower than the actual rest length that we are considering, then there will be the springs will start to push these points away. And when they are pushed away, the power law will tend to bring them back together in an incident position. Okay, and then in that case, the spring will act once again to separate the points. So it's some contrast between these two components. It's the balance between the two that gives us the circle packing. Okay, so if I run this again, you see that here we have our perfect packing of these circles. Well, not so perfect because you see that there is some overlapping. This is because we have, for example, some, let's say, the action of the power law is too intense. So if we decrease this, we can easily find, for example, a balance between the springs and the power law. Now, what's the use of this? Well, it has several uses. For example, in jewelry, this is something that you use for covering a surface with a set of gemstones, okay? And this is a very particular structure, which is quite difficult to achieve, especially when later on, in a few moments, we are going to replicate this kind of behavior over a organic surface, okay? So when we work inside a plane, well, there is no particular problem because we simply have to program this kind of interaction, okay? Yes, that's exactly what I wanted to do right now. So we are going to change this situation now, and we're not going to work with one single radius, because if we work with one single radius, things are quite easy, right? So we already have it. But I was telling you that this kind of simulation here is not difficult from a conceptual point of view. It's difficult, it starts to be difficult from a data manipulation point of view, okay? So if you work with one single radius, it's very easy because you just have to multiply this radius by 2, because you only want circles which have all the same diameter, okay? So the circle packing is basically given by this value here. Eventually, what you can do is also use a multiplication factor, like between 1 and, I don't know, 5, okay? And if you set this to 1, you see that we get the flower of life, you see? And if we start increasing this, then we can program the separation between these circles in a dynamic way. And also we can have them like physically separated, but also always in a packing configuration. Okay, so this is the maximum that we can do in this case. Okay, and it's very easy because we are just considering what's the we can bring this back to 2 if we want a circle packing like this. Oh, and by the way, even if the intensity, the strength of the power law is too high and produces some overlapping, I do recommend that you initially keep this like with higher values, because else you see that the simulation is quite slow. Okay, so you see that now with this strength, I can easily increase or decrease. You have almost a real-time interaction and a real-time result. Okay, so keep this higher than you would eventually, and then once you have the equilibrium status, then you just decrease this value to avoid extreme overlapping. Okay, but anyway,
Giancarlo, excuse me.
Yeah.
One question. In my case, the packing begins to join in just one single circle.
Well, in that case, probably either you didn't connect the upper cutoff.
Yeah, I got it.
So remember that this multiplication here defines not only the rest length, but also the upper cutoff for the springs. Either this, or you're not working with springs at all. So remember that if you don't work with springs, of course, this point will collapse together into one circle. Either
Okay, let me double check. Right.
Yeah.
Thank you.
Yeah, you're welcome. But it's just I am sure it's just a matter of connecting wires. So I don't think it's a conceptual problem. But anyway, so the real problem is what happens when you work with different radius. So before Hitesh get into a random radius, let's start working with just a couple of radiuses, because this is the real problem happens when you just increase the amount of desired radius to 2. Okay, from 2 up, it's always the same solution. Okay, so let's start with something simple, and then we increase the complexity. So I will I will copy paste this because I don't want to waste time with the initial part, and get rid of this first solution that we came up. So this is simple circle packing. Okay, well, I should start writing something here like circle packing 1 radius. Okay, so we can easily recognize what happens inside this thing. And let's add this to the group. Okay, so let's go back to our, let's say, population of points. I will start with few points as always, and always in order to keep things, let's say, clear. So we have this population of points, and now I want, for example, 1 radius and also another one. Let's set them to 2 and 4, for example. Now the problem is that, first of all, the fact that we have 10 points and two values for radiuses forces us to first define, well, how many points must receive the value of 2, and how many points will receive the value of 4. So how many circles will have 2 as a radius, and how many circles will have 4 as a radius? Okay. Remember that interconnection are just the spring aspect. Okay, so the attraction or repulsion. But now we must define the radiuses. Okay. So because why do we have to define the radiuses? Because when we work with a population of points, oh sorry, a population of points, okay, and we want random or different radiuses, the mutual distance between these 2 points, like this distance here, is not going to be twice the amount of one value. It's going to be the addition between these 2 values here eventually. So there are basically 2 possible situations here. Either we have 2 closest points which share the same value of the radius, and so we have, for example, 2 plus 2 as the distance in that case, or we have 2 points that receive 2 different values for the radius, and then we have 2 plus 4. So the distances in this case can be 4 and 6. And so this is the problem. Okay, so how can we determine that the spring acting between different points is going to have this rest length or this rest length? So this is the data manipulation problem, okay, that we are going to solve in a few steps, but it's somehow we will be going back and forth with panels in order to understand what we are doing. Okay, so just follow me, and if you get lost, just tell me. It's going to be a few steps. If you want, you can also save your questions for the last step, but it's something that it's going to be quite dense. Okay, so first of all, I want to have, if I have 10 points, I need 10 radiuses. Okay, so it's going to be a mix between these 2 values. We can do several things in this case. We can use a repeat data component, for example. So I want to repeat 2 and 4 until I reach this amount of repetitions. So repeat data is actually taking the values 2 and 4 and repeating them until the list becomes 10 in length. And so we get this 2, 4, 2, 4, 2, 4, 2, 4. And if I increase this, I will have more and more 2 4s, like 33 values in total. Okay. This is one possibility that we have. The other possibility is to use, for example, a longest list method, which is a standard in Grasshopper. In terms of data manipulation, the longest list method is something that happens normally. So if I have this population of points and I want to create a circle and I use them as a radius, okay, and I just plug one radius to this, I'm using already here the longest list method. So here we have 10 values in the first list and one value in the second list. Longest list make these two objects, these two sets of data interact like this. So if we take a panel, I told you we were going to use some panels today. So this is the first set, and this is the second set, okay? And they are interacting inside the circle component, the circle function. Longest list say that when you have a list which is longer than the other one, the amount of interaction is determined by the longest list. That's why it's called the longest list method, okay? So what does it mean? It means that normally you will have the interaction between this point here and this radius. So you will have one circle. But then there is the longest list method that says if you have more elements inside one list, you make the last element of the shortest list interact with all of them. So basically what happens here is that you have the first circle coming out from this one-to-one interaction. But then as there are more elements here, and you don't have any more elements in this list, then the last element of the shortest list will also interact with all remaining elements of the longest list, okay? So this is what happens with the longest list method. It's something which is natural in Grasshopper. It's the default interaction method. Now, saying that we want a longest list method in the explicit way means that we have a list of values, like this one, which is the point, and we are providing another list of values in B. What can happen in this case? Either the list A is larger than the longer than the list B. Then in that case, list B is basically expanded to reach the same length as the list A. Or list A is shorter than list B, and then it's list A that is being expanded to reach the length of the list B. Why this is more interesting than the simple repeat data? Because repeat data actually create or tends to create the same instances for the values that you are connecting. For example, if we have 10 as the program list, the program length for our list, and we have two values, we know that as we have two values, there will be 5 2s and 5 4s here, okay? While the longest list gives you some more possibilities. Repeat last means take the shortest list, and in order to bring that list to have the same length as the longest list, repeat the last value. This is something that is the standard behavior in Grasshopper. Okay, so if we take a look at what happens at list B, because it is the shortest one, we will have the first value is repeated once, and the second value is repeated as many times as needed to get the length of list A, so 10 values. The other options is, for example, to switch, right-click on longest list and switch to a different approach, like repeat first. If you want, for example, all your circles to have a radius of 2, but one that must have the radius of 4, then you switch to repeat first. Then there is interpolate, which is the one that we are going to use. This is something like repeat data, because we want to repeat these values here more or less the same amount of times in order to get to the length of list A. So this is something that already happens in repeat data, even if they are repeated like in a true-false pattern, like you repeat this list and then repeat it again and again and again. So you have 2, 4 repeated 5 times in this case. In this case, you have simply 2 repeated 5 times and 4 repeated 5 times. This is something, for example, that it's also valid if you have 11. The interpolation happens with integer values, of course. You cannot have like 5.52s and 5.54. You have 6 2s and 5 4. Okay, and so on. So I think that longest list is more interesting for us. You have a couple of other options, but you can simply investigate them by yourself. It's not that relevant for us in this moment. So let's say that we use longest list. Now we are deciding that half the amount of points will have a radius of 2, and the other half will have a radius of 4. Okay. Now the problem, what's the problem? The problem is that these points are random, so we don't know which point is becoming which circle. So, for example, in order to take a look at what's happening, you might take the points and give them their radius, and you see that you have this random distribution of circles, small circles, and big circles. Okay. So the problem is that when we create this interconnection, we don't know at the beginning what would be the appropriate rest length and upper cutoff for these connections. Okay. So in order to do this, here comes the data manipulation part. Okay. So first of all, what we want to do is take the interconnections lines and do something like this. I'm going to calculate the endpoints. Why I'm going to calculate the endpoints when I already have them into one single point cloud? Because these endpoints are coincident with this point that are already present in the populate 2D. The reason why we do this is that these points here are not related to a random population. They belong to the interconnections. So with these endpoints, we know if this is a spring, basically, we will know which point belongs to that spring. Okay. So once we know which point belongs to that spring, we can, for example, relate, for example, this point here with one of the radiuses that come up from here. That can be 2 or 4. Let's say it is 2, for example, and the other point with the correspondent radius that might be, for example, 4. So in that case, once we know this relationship between these 2 points, we can just add 4 to 2, come up with the relative value here, and use it as rest length and upper cutoff. Sorry, upper cutoff. Okay, and this is going to happen for each interconnection. Okay, now what's the problem with this? The problem with this is the way that data are sorted inside these things here. If I use simply endpoints applied to interconnections, what I get here is all the start point of my interconnections. And here we have all the endpoints of my interconnections. This is useless, okay? What I want is the start point and the end point per each interconnection. So I must graph this. If I graph this, what I'm getting is that each branch contains the start point referred to one interconnection line, okay? So if I take, for example, these 2 panels here, I know that branch 000 of this data tree and branch 000 of this data tree contain the start point and end point of one interconnection line, the first interconnection line, and so on with the following branches. Okay, so what if I bring this output together? If I bring this output together, and this is possible because you see that we are getting the same path for each branch, okay? So if I merge these 2 wires together, the endpoint will be merged in the same branch as the start point. This is only valid because we have the same path, okay? So pay attention to these details when you merge wires together. So here we have 2 points, which are start point and end point of each interconnection line, okay? So this is very important. Now, the problem that we have is how do we, so everything is clear right until now. So it's very simple until now. The problem is, how do I connect the correspondent radius to each of these 2 points here? Because these 2 points appear in a random population. And I need to define if this 0 here, this point here, is receiving a 2 or a 4, and if this one is receiving a 2 or a 4, okay? So in order to do this, what I must use, well, let me grab this panel and move it like here at the bottom. We are going to use several panels right now, and I'm going to lead them so you will be able to see the history of this script, okay? So what I need to do right now is understand when these points here appear in our population. Okay, so I will use a component which is one of the not so friendly component, which is called member index. Okay, so what I'm going to do right now, I'm going to plug the members, which are the points that I want to understand how many times they do appear in my point list. Okay, and I have to tell this member index what's the set of points that I want to use. And the set of points that I want to use might be the output of the population of point. Okay, but there are several situations that can happen in this case. So, for example, what happens if for some reason we have more radiuses than points? Then in that case, there will be more points than the population, right? So list A contains 11 points, which is exactly the same population that populates to D, because the amount of radiuses that we are using is smaller than the amount of points that we have. So there is no repetition of the initial points. But if for some reason you want to use more radiuses, then the amount of points in list A will be higher than the amount of points of the population. And in order to keep things under control, it is better to use the list A output, because this can be variable. So I will use this as the set of points that I want to check as the set in my member index. And now let's see what happens with this, because this is the tricky part. Okay, so index is very interesting because let's take a control panel here, like this. So index is saying, okay, so your start point of the first interconnection corresponds to the point with index 0 in your list of points. And your end points, because remember that we have the end point, the start point and end point in one single branch, and the end point appears in this set of points as point number 1. So if we take another panel and take a look at this list A, what this member index is saying is that the first interconnection happens between point 0 and point 1. Okay, then there is the other interconnection. You see that this member index, as it must come up with one index, it splits the branches. We have basically 2 elements per branch here, and now we go back to 1 element per branch. But remember that in Grasshopper, the order of data inside the data structure doesn't change unless we want it to change. So we can assume that this element here refers to the start point of the first interconnection line, and this element is the end point of the first interconnection line. And then we have second interconnection line, and then we have third interconnection lines, and so on. So if we want to regroup the indices by interconnection line, what we can do is an operation, a data manipulation operation, which is called shift paths. Oh, by the way, there is also another shift paths, which is this one, which is called shift paths minus 1. This is basically an automatic version of this. This shift paths allows you to define an offset, which value is set to -1. And we are going to see this in a few seconds. So if you want to perform a standard shift paths, there is also a shift paths -1. Actually, I'm not sure this is a standard Grasshopper component. Yes, I think it is. Yes, they are all, well, I'm not sure. No, this is from Daniela Balde, which is the developer of Peacock, which is a plugin for jewelry design. So this is not a default Grasshopper component, while this one, yes. But anyway, we need to shift paths by -1, so we can also use the standard behavior of this shift paths. If we do this, what we get, let's grab another panel, what we get is this. We are going back to this data structure, 2 elements per branch, but this time we have the indices that corresponds to our points inside our population. Okay, so let me further discuss this. I'm going to take a param viewer. So we have this data set here with this amount of indices in the definition 4. So you see it is 0, 0, 0, 0, 0, 0, 0, 1. Then you have 0, 0, 1, 0, and 0, 0, 1, 1. Then 0, 0, 2, 0, 0, 0, 2, 1, and so on. So it's clear then that these two branches here come from one single path, and they are split into two additional branches. Okay, so when you shift path -1, you are getting rid of the last variation of the indices, and you are sticking with the previous path. And so two different elements are going to be grouped in the same path, which is going to be 0, 0, 0. And then 0, 0, 0, 1, 0, 0, 1 will group these two elements. So this is the meaning of shifting paths. So if I also duplicate this and plug this here, you see that now we get rid of the last variation of your indices in path, and then we are grouping two elements per branch. Okay. You can also see it graphically. You have one level of separation less than the previous three. Okay, but anyway, this is the more important visualization for the parent viewer. Let me grab this and bring them close to our panels so there is no confusion. But I hope there is no confusion. But okay, so these are the three steps that we have right now. Now, what I want to do, now that I know that point, for example, the start point of the first interconnection line has index number 0 in this list of points. But the list of point A has the same length of list of radiuses B. So we are already connecting one point to one radius here. So what happens if I do a list item, okay? And from the list of radiuses, I want to extract these indices here. So let's see what's the result of this list item. I'm going to grab another panel and connect this. Now there are few things possible here, just two things. Either that point corresponds to a 2 or it corresponds to a 4. And you see that the first interconnection happens between 2 points that share the same radius. But then you have 2, 2, 2, 4. And then you have 2, 4, 2, 4. And it might happen that you have also 2, 2, 2, 2, 2, 4, eventually some 4, 4. Yeah, you have also some 4, 4. Okay, so what we are doing here is understanding how many times the endpoints of your interconnection appear in the set of points that you have from the population, determine what's their index inside the point list, which is this one. So I can also grab this panel and move it like here because this is one single step. And then there is the shift path because we want to regroup the indices per interconnection line. And then we have the list item, which is basically taking the correspondent radius to the endpoints of the interconnection lines. So we have a couple of radiuses which are basically connected to one interconnection lines, which is exactly what we wanted to achieve. Okay, and here we have the group. Well, basically the same point, but they are grouped by interconnection line. Okay, I hope this was clear enough. The next step is to take this couple of values here and perform a mass addition. We could also do a, I don't know, a dispatch these two values here, one in one branch and one in the other branch, and then create a an addition here like this. Okay, but mass addition just adds all the values that are present in the list, so it's more immediate to do this, and the result is going to be this. And these are exactly the radiuses that we want per each point of our point cloud. Okay, so finally we came up with the rest length actually. Okay, so this is the final step. Once we have the rest length, you see that these are 55 values because we have 55 interconnection lines. This is a list of lines. So in the end, we will need a list. So we flatten this result. We will need a list of distances. Okay. And finally, once we have this, we can finally go into Kangaroo 099, grab the spring from line, take the connection and use this as the connection for the springs, and use this value as both rest length and upper cutoff, as we saw in the previous definition, the simple one. Okay, so all of this thing here is needed to define the springs in this case, and we are only working with 2 radiuses. Okay. And the other thing that we must do is, besides getting rid of our preview because it's not relevant, is program also the power law, which we use, by the way, the same interconnection. This is always the same, so there is no problem with this one. We want this to be an attraction, so let's negative strength a slider. And then we take the usual merge component, make it a little wider, and then merge springs with our power law. And then we grab the solver, and then we plug this with flatten inside the force object. It's important to flatten this because there is no guarantee that these 2 flows here of data have the same paths. So for example, even if they are simple lists, if you take a look at this, you see that also a simple list might have a complex path with more than 1 index. So if the 2 paths have a different amount of indices, they will not merge into one single list. So that's why it's important you flatten this output. Okay. And then we have this Kangaroo physics already set up. Let's play this. And you see that now we have these points that are getting close together, but with different separation. Now, in order to understand what we're doing here, it's probably more relevant to create circles after the simulation with particles out, which are our points. They are in the same order as the original longest list. So I will use the radius coming from the list B. Okay, so list B is going to be plugged to radius here. And then we have these variable size circles packed inside our original area. Okay. Of course, you can also, in this moment, you can change these 2 values here and have a different situation. Okay. And this definition here, the new definition that we just created, can also work with a constant radius. Of course, you can also set this to 4 and this to 4, and then you have the original circle packing with this equilateral triangle separation. Okay, but this is quite more interesting. And so from this point on, you can basically decide how many different radiuses you want, because there is the longest list. This longest list is doing the job, actually. Okay, so it's basically spreading your radiuses values between the population of points that you want to consider. Okay, so if I stop the simulation and I don't know, like increase the amount of points, and I also want, for example, to add other radiuses like this, and so I plug this here and add them to this group. So yeah, they are inside the group, and then rerun the simulation. Now we have 4 values, so I can also take this and also take this and change it. So we have 4 different values for our radiuses. So from 2 up, this is the construction, the definition that you must create. So there is quite a bunch of data manipulation, but it's at the same time it's data manipulation, but also conceptual, because we are basically stating something here that is using the same population, but divided by interconnection line, because in the end we want to come up with the mutual distance between points which have different radiuses. Okay, so you see that now we have here a little more variation inside the possible distances that we get, but you see that they are always the same values repeating. Randomly, they are shuffled because we are working with a random population of points. Okay. So this is something that you might want to use. For example, going back to the jewelry example, you might have, let's say, different sizes for your gemstones, and then you just program them here. Like, I don't know, I want gemstones between 1 millimeter radius, 2 millimeter radius, 3 millimeter, and 4 millimeters, like this. Now, one thing is that you change this on the fly during the simulation. The other thing is that you rely on the random distribution of your points. And so it's different from having them already packed and then changing the radiuses, then changing the radiuses and then pack the circles. Also, in this case, it might be useful to reduce the power law intensity, because if you have too much strength, it's normal that the smallest points or the smallest circle tends to stay on the inside, okay? Because they tend to, let's say, pass between the small spaces left by the bigger circles. So if you decrease this value and you let the simulation run but slowly, then you might also get this kind of distribution where the small circles are more evenly distributed inside this pattern. Okay. Once you have this, then you can go back and increase a little the intensity of the power law, because this is it's difficult that this operation will change the equilibrium. It will only pack the circles more and more. Okay. So in order to get a proper result, maybe you might want to start with a low value for power law and then increase it during the simulation of life. Okay. So basically, as you can see, this is something that in Kangaroo 2, it's something that you might think of reproducing with collisions. Okay, there is no collision happening in this definition. This is the Itesh.
Yeah, the exact thing what I want to ask, the same thing, like in the recent version of Kangaroo, how we'll be using it.
Yeah, exactly. That's the point. Now, you might think about collisions in Kangaroo 2, but here there is no collision. That's the point. Okay, so first of all, there is no collision here because there are two forces that are acting in the opposite way. So the power law is attracting the points together, and the elastic force is basically a repulsion action in this case, okay? Because it only works when the springs become too short, and then they tend to recover their rest length, which is larger than the actual distance. So it's an equilibrium, it's not a collision, okay? While in Kangaroo 2, for example, one might think, okay, I have these points here, and I can use the spherical light. You cannot use spherical light because spherical light only works with one radius. So spherical light works perfectly when you have one single radius. That's what we were doing before. So in that case, you can, for example, use in Kangaroo 2 the same interconnection, convert this into springs. You can also give these springs like this. You can also give these springs a rest length of 0, so they tend to contract indefinitely. So they will always apply a contraction strength, okay? But then you can use the spherical light and use, for example, let's use a populate 2D here. So you interconnect these and use these points here with a spherical light with a given radius of, I don't know, something, okay? And then merge these two components together, and you should get the same behavior. But the problem is that these only work with one single radius. Later, we are going to see how eventually we can work with different radiuses, okay? In another example that we are going to do in, well, eventually after the break, because first I want to start another simulation with. But this should be the equivalent with Kangaroo 2 as regards the one radius problem. So circle packing one radius. So I will eventually group it with these and yeah, Kangaroo 2. Add to group, and then take these and add to this group. Okay, so this is the Kangaroo 2 solution. You might want to try and play with this and see if it works. It should actually, but see if it works. So this is quite important. Okay, so this is the thing that we are going to use in the next cases, because there are going to be some particular cases, but I want you to understand that there are many possibilities that you can, let's say, solve, many cases that you can solve with this very same definition. Okay, so let's yeah, okay, so like this. So this is the actual definition when you want circle packing. This is circle packing with.
Carlo, I just want to ask one thing.
Yeah.
Actually, I used this exercise before. I tried it, but I didn't actually get how to get this result. Basically, I used this Kangaroo 2 as you showed on the top, the components. Those are the same components what I used. But the main thing is they're not actually interconnecting each other. So it's what I mean is like it's like when we use the distances of the lines, everything, and we actually these circles are actually connecting each other.
You mean these distances here?
Yeah, these distances are actually like connecting each other with these parameters what we used in
Yeah,
with the old Kangaroo.
Yeah. The problem with Kangaroo 2 is just using different radiuses. So in this case, we came up with a general solution which works. And the problem with Kangaroo 2 is that as you don't have the power law component, because it is no longer present, then you must come up with a different solution in order to consider different radiuses. You cannot do it with spherical light. We will find a way to do this in another with another strategy. Okay.
Yeah, exactly. I think this power law is actually missing in that component.
I love power law. I really love power law. I don't know. I don't know why it was deleted from the new version of Kangaroo 2. But anyway,
And
you
I
must do some
just
workaround. Sorry.
and I just want to ask, and I just want to add a layer, which is like if you're having a circle and if you're populating the points inside the circle, and only the collisions will be inside the circle.
Inside the surface.
Inside the circle. If you are taking a circle as a boundary, and inside, if you are populating the points and giving the this circle with the different radiuses and colliding with each other, and can we generate something like that?
So you want these collisions, for example, to happen only inside a given surface, a given boundary.
Yeah.
And if the points go out from that boundary, you don't want them to collide anymore.
They can collide the boundary, but they can't come outside. Something
Oh,
like that.
you want these points, for example, to don't exit, for example, a given boundary.
Yeah.
Well, actually, you can do this in two different ways. First of all, consider that we are using a power law. So these points will always tend to stick together, okay? Second thing, we are using a populate 2D, which is based on a rectangle, okay? We can always, for example, let me get rid of this. You can also always switch, for example, to another thing like, I don't know, point, set multiple points, and create a NURBS curve, which is going to be periodic. And let's create a boundary surface. So what we have right now is this geometry, this surface. We have the boundary, which is the curve, but we also have the surface. So relying on the fact that these points will always stick together, we can also use the populate geometry and populate our surface with this point cloud. And we can always switch to this and release the simulation from this actual configuration. Okay. Now, problem is that in this case, let me just visualize the boundary. Okay. As these points are basically all collapsing, basically, they tend to occupy only the central part of this geometry. In this case, for example, what we are going to reproduce in case you want to simulate, for example, collision with the outer edge, you must increase this. So you are saying, I don't want, for example, these points to go out from this curve, right? That's the problem. Okay, so this is what you want to avoid.
Yeah, this is what I want to have.
Yeah,
actually.
like these points going out from this boundary. Okay, so in case of, let me pause this simulation, okay? So in case of Kangaroo 099, because once you work with one version, you cannot mix forces and goals from different versions, okay? So this wouldn't understand goals coming from Kangaroo 2. So I'm switching back to 099. Here you have, let me see if, let's move this. Okay. So you want these circles to stay inside your given area. So let me see if we can do this with some constraints, because I don't see any line. Well, this is not working. This would not work. I would say that you must pull your points to the mesh. This is probably the easiest thing that that we might do. Let me see if there is something else. No, I don't see anything else that might work. So I would say, for example, pull to mesh could be a solution. So let's try it. Let's see what happens. Let me move everything here. And what I want to do, I want to also force this, well, actually not these points here, but the points that are involved in the simulation, which are this one. And the constraint mesh will be a mesh. Oh, by the way, in this case, for example, we have a little problem because this mesh, as it comes from a boundary surface, it's a trim surface, you see from the output. So if you try, for example, to mesh surface this thing, you will get this. So according to the resolution that you give to this object, you have this segmentation, these faces that come up, which are the polygon of your mesh. And if the polygon intersects the surface, it is kept. If it doesn't intersect the surface, Grasshopper doesn't consider it. Okay. There are some control. You have the overhang, and you can see that in this case you are inverting the situation. So you are considering only the polygons that are fully contained inside the surface. So you don't want this, because in other case you don't take into account the boundary. Okay. So what you might want to do in this case is do another thing. I say this, I name this like surfaces that are in contact with their inputs. So this boundary surface is not in contact with its input, because the curve is only taken as a trim object. I want this curve to become exactly the edge, the real edge of my surface. Okay, so in order to do this, I would calculate, for example, the area, as this is more or less a convex shape. And I would do, for example, an extrude point. If I extrude this curve towards the center, I get basically this surface is a flat cone, right? Because it is extruded towards its center. You see that there is an edge appearing here. So this is a flat cone, but as the curve is a smooth curve and continuous curve, as an extrusion, you get one untrimmed surface. So if I mesh surface this one, I get a mesh that corresponds exactly to the boundary. So if I increase, for example, U count and well, actually not U count, but V count, which is the original curve, I can increase this and have as much resolution as I have, and take into account exactly the boundary of my initial region. Okay, so this is something that has to deal not with data manipulation, but with topology that you must take into account if you want to get to proper result. So I will switch this, move this here, and I would say this is the mesh I want my point to be constrained. So if I do this, let's check that it works. Let's reset the simulation, and let's run the simulation. Well, actually, the points are basically contained. You see that the points are inside the, well, they might be going a little out. This is because of the pull strength. So if you want this to be more effective, you get a one-on-one slider here and eventually increase this. And you see that now the points tend to stay on the inside of your region, okay? So if you want the circles to stay inside the region, what you can do is basically create either a offset of your initial curve. So you say, I want to stay inside, and program the offset to use the larger radius that you are considering. So for example, if the larger radius between these four, well, you can use a min-max component from Heteroptera, for example, where you easily have access to the min-max. You just plug all your radiuses to this min-max. Let me stop the simulation for now. So you have this, the maximum is 593. And then you can offset curve. You take this one, you offset it using this distance negative, because you want it to be offsetted like inward. So expressions minus x. You don't want to see this curve actually. Okay, you just want to have an idea of the original region that you are considering, but you will use this curve for the well, actually just for the extrusion, right? Just for the extrusion. So you have this extrusion, this mesh is going to be smaller, okay? And then you run the simulation and you have your point inside your region. And you can increase the amount of points. Of course, there is something that you cannot do parametrically, which is to understand, because you see that there are some empty spaces here, no? And you can fill them with more circles, of course, but there is no chance for you to understand how many points you need. So you must, this is like some back and forth between trial and error that you must perform. So you see that there are empty spaces, so you stop the simulation, you go back to the initial part, and then you take the populate geometry and populate it with, I don't know, and a 101 slider, because this is actually 100 points and it's not enough, so you need more. And you start, for example, increasing this like 100 and, who knows, 30. Well, I think I exaggerated, because this ladder goes up to 1,000. And eventually, I would say, no, you go up to 200. And now I want 130 points. Okay, so if you run this again, well, you see that more or less 130 is already starting to be something. And in this case, for example, what happens is that there is very few space for these points to adjust during the simulation, okay? Because they are already filling the space. So there is almost no possibility during the simulation to adjust the distribution of the different radiuses. What you can do eventually in this case would be to play around with these values here, because dynamically this will adjust.
Maybe we can use Galapagos to minimize the
No,
circles.
you can't do this, because remember that the amount of point is a geometric property for your system, and Kangaroo doesn't like geometric editing of the system in real time. Okay. So
yeah, thanks. That's interesting, actually.
okay. So yes, that's the maximum that you can do in this case. But I think that it's already quite a good solution. I I have no other ideas for the time being. So so yeah, basically that's a more general approach. Of course, we can also get rid of the original populate 2D, because now we can simply create a rectangle if we want a rectangle, or whatever type of a surface if we want it to work inside an organic shape. So let's go back to our definition. Let's see what we can do with this, because this is just the beginning. Actually, particle packing is one problem that goes around since years, actually. And Kangaroo has been actually besides scripting, I mean, not visual scripting with Grasshopper, but real scripting, coding. Besides coding, Kangaroo is one of the more efficient way of creating this kind of behavior, like circle packing. Now let's apply this circle packing to different situations. Like, for example, what if we want to have this circle packing over a given surface, organic shape, for example. So let's quickly create a shape here in Rhino. I'm going to create a deformable plane, and then soft move its control points. Yeah, wait a second, Yitesh, let me do this. Okay, something like this. Yeah, tell me, Yitesh.
Yeah, I thought before going to the next part, can we manipulate this lens, what we have done this in the last exercise, with mesh machine?
With mesh machine, in order to do what?
So in the same way how we have the lines, like with the particular lens, and we defined it, and we have given the radius of it. So in the same way, can we take the mesh machine vertices in a defined particular length?
Well, actually, when you we will be using mesh machine tomorrow, probably to perform some preliminary operation over another problem. Eventually, for those of you who don't know what mesh machine is this component here that basically is used to remesh a geometry, a given geometry, with some controls. So you have several controls over this in this component. One of these is, for example, the length. The target edge length, as far as I know, is one single value in this case. So eventually you can, I don't know, probably you can manipulate the point distribution in order to adjust the mutual length or mutual separation, and then use the given point cloud to create some mesh, probably. But I don't know if you can work with a mesh machine. I never tried this. Maybe we can also further investigate this in a separate session, Hitesh.
Okay, okay, thank you so much.
So I'm going to take this surface here and use it as a base surface for an additional condition for our circle packing. So I'm going to internalize this value, and I'm immediately going to mesh surface this because you know, Kangaroo and surfaces, they don't get along. So basically we have this open mesh, and I want to use it in order to produce some kind of circle packing onto this surface. The higher the resolution, the better it will work, actually. Okay. Now, this is something that actually we already implemented, because having our point cloud or circles, let's say, contained inside a boundary, we solve this problem exactly the same way that we can solve this belonging to this surface. The only thing that I would do in this case would be eventually substitute this mesh with the mesh that we were using here on top. So let me just Control-C, Control-V this, and move this mesh here in this area. I'm also going to reactivate this part of the definition. And what I want to do is to constrain all my points not to this mesh. So no extrusion, no offsets, no min max, nothing of this. So I'm going to use this mesh here. So if we do this, during the simulation, these points will be sticking to this new mesh. Of course, if we start with this huge population and also with a distribution of points that has nothing to do with this geometry, things can become quite, let's say, irregular. Okay, so I would say that eventually, instead of populating this boundary here, I'm going to get rid of this as well, and I'm going to populate this surface directly with less points, like 50, for example. No, well, no, even less. So let's start seeing if things go and work properly. Okay, so this is what we are going to do. I'm going to also organize things a little more. So this mesh is going to be here. So if we do this and we run the simulation, we have let's say a circle packing. But if we see this from top, or well, my top view is not working actually. You see, yesterday we were discussing this, but if you see this from the front, you see that the circles are being created like horizontally because the plane is just defined by the particles. Okay, so eventually what you should do should be like create a surface closest point, which is a projection of this particle over a surface, and use the initial surface like the projection surface in order to determine these vertices. Now, this is apparently it's useless because actually if you have a point lying on a surface and you project the same point on the same surface, you get exactly the same point. But if we do this projection, we get this parameter here, which is called the UV point. Now, when you want to access parametric aspect of a given geometry, be it curves or surfaces, it's the same, you must reparameterize the geometry. So for example, let's take a look at the result. We have point with these coordinates. You see that they are still changing because the simulation is still running. If I pause, we stop this. And then you have UV point. And you see that the coordinates are always like big values. Okay, but if I reparameterize the surface, the UV point has coordinates between 0 and 1, always. Okay, now the UV point is very useful because we can also do another thing, which is evaluate surface. So the surface I'm going to evaluate is still the initial surface, like this, and I reparameterize it because I want to work with the U and B coordinate system, which is an internal parametric coordinate system, and use the UV point to evaluate this surface. So this is giving us the frames. The local frame is a frame which is tangent to the surface in that point. And then we can use these frames as planes for our circle. So if we do this, what we are obtaining is circle packing onto our surface. Of course, if we work with huge radiuses, then the circle is going to be tangent to the surface in the center point. So it's going to raise up like this. And you have these connections in the tangent areas between the circles. But if you work with a more proper values for your circles, like, I don't know, decreasing these, which are the biggest ones, then you can say that more or less you have the proper tangency between your circles. You see that now, for example, Kangaroo is moving like this, and this is because the simulation is in pause. I can play the simulation and have this happening in real time again. Okay, so here you can use an underlying surface in order to program this circle packing, but you also have to orient the circles onto the surface. So you had to do this kind of tricks here, like surface closest point and evaluate surface. Always reparameterizing the surface because you want to work with parametric coordinates. If you don't do this, if you don't reparameterize, these circles start to fly around because you are working with geometric coordinates instead of parametric coordinates. So, but this is something that has to deal with topology, and we are not going to further discuss this. Okay, so the problem is basically the same. In this case, you are already considering an underlying surface, so there is no need for considering I want these circles to stay inside the given surface because they are already being projected or pulled to the mesh. Okay, so you are already solving the two problems. So lying on the surface and staying inside the surface. Remember that the only thing that you cannot do is understand how many points you need with those random radiuses to fill this object. One thing that you can do, for example, in order to let's say simplify this longest list calculation here, instead of using separate sliders, you could also use a gene pool from Galapagos, which is basically a set of sliders providing one single list of values. So you see that this is what's happening. And of course, these are radiuses, so you must edit this thing in order to understand how many different radiuses do you need. For example, I want 5 values. Do you need decimals? Yes. What is the minimum value? Well, eventually 1. What is the maximum value? Eventually 5. And then you have 5 sliders between 1 and 5 that you can simply adjust as you please. And you plug this instead of your sliders in the longest list. This is a more efficient way of creating this list of values as for the radiuses of your circles. And at any time, you can also edit and add more sliders if you need. And yeah, basically, so this is a more interesting, let's say, definition, a little more organized. Okay, so this is the way we can pack circles over a surface. Remember that we are discussing also plane and surface and space filling strategies. So this is a surface filling strategy. Okay. So it's very simple. You just need to change the outline that we were considering before with a given 3-dimensional object. Okay, so it doesn't change almost anything. So circle packing on surface, for example. The interesting thing is when you want to concentrate, for example, this circle packing in very specific configurations. So what we are doing right now, as we are using the power law, is that the point tend to collapse altogether. This is something that looks like an attraction to a point, right? So let's do this. Let's use, for example, 2 different criteria. We know that we are working with opposite forces. The power law is attracting points together, and the elastic force is basically a repulsion force. Okay? What if they don't work with the same connection lines? In the end, we can do this because the springs always start working when their rest length or when their length gets shorter than their programmed rest length. Okay, so it doesn't matter where is the attractor in this simulation. Okay, so let's see what happens, for example, if we start programming things in a different way. So I'm going to take a populate 2D. This is going to be valid also in 3D, but let's start with 2D and also with fewer points like this. So the power law, we already know about the power law. We can easily program it. It's very simple. We interconnect points and use this. Okay, this is what we have been doing so far. But what if I want to collapse this set of points not towards the center or the barycenter, because this basically the power law is mixing all the attractions together and tends to concentrate the points in a, let's say, intermediate region, more or less at the center of this point cloud. Okay, it depends on many factors, but more or less this is what happens. Okay, but what if I want to concentrate these points like here in another region of our plane? So instead of using these interconnect points, which are only used to determine the springs behavior, and we have also used this to program the power law, but in this moment I don't want to use this. What I want to use is, for example, the connection between this population of points and my, let's call it the attractor point. Okay, so I'm going to create a set of lines between this point and this point cloud. And I want this connection to be our connection for the power law. So if I negative this strength and set it to, once again, 5, so -5 strength attraction, and these are the connection lines, and this is the attractor. Okay. All the rest stays basically the same. So I won't go through this thing again. Sorry. So I'm going to simply copy paste all of these things. Also the interconnection eventually. So the points are going to be the list A. Interconnection, we already have it, so I'm going to substitute this with this. And eventually here we already have our setup for the springs. So springs and power law. So you see that springs are working with the interconnection and power law is working with disconnection with the attractor point. Okay. So what happens in this case? Let me just also copy paste these merge Kangaroo. I no longer need this. I just need a circle. So our goal this time are power law and the springs. I'm going to get rid of D3. And what I want to use for the center is the particles out. Ring radius is going to be, as you know, the list B for our longest list. So if I do this, I should have a different behavior because our points are originated inside our rectangle, as you can see. Actually, in this moment, you see, for example, that also the attractor is being treated like the center of a circle. This is not correct, right? Why? Because when we use, for example, this point as the origin of all these lines, and we use this point also, therefore, for the power law, what happens is that this becomes a particle for our system, okay? So if I use the particles out, this point will be included in the generation of circles, but this is not correct because we have 12 particles with just 11 points in our population. So in this case, what I need to do is take the points that come from the list, the longest list, plug them inside the geometry, and use the geometry out, which are only the desired points, like these ones. Okay, so you see that there is a let's say difference between particles out and of course geometry out. So I'm using the original population as geometry, so to have it available in geometry out, and then we can run the simulation. If I run this, you see that now this point still are still sticking together in that position. Let me also see if I tend to increase this. Why it is not affecting this? There is something is not working properly in this case. So this is correct. These are correct. The endpoints being eventually, let's take this list here. No, we're still dancing around this area. And also there is something that, oh yeah, of course, rookie mistake once again. So it's plenty of stuff to remember, sorry. So in this case, for example, what happens is this, take a look particularly at this point here. If I let me hide these points here, and how can we do this? Particles out are actually, I want to isolate these points somehow visually because I want you to take a look at what happens. But I should partition some lists. Well, let's take a look at what happens to this point. Just pay attention during the simulation. There is one point, this one, that is moving around, and there is no circle. You know, this one. So this one is actually our attractor point, which is basically reacting with all the rest of the points because it is subject to the power law. But the power law, remember that it tends to concentrate all the points in one specific area, which is the center of mass, basically. So the center of mass between all these points here and this one here is located more or less in the same area. So in order for this to work as an attractor, I must also take this point and use it as an anchor point for my simulation. So this point cannot move during the simulation. And now if I do this, this point will be attracted to that region correctly. Okay? And it's nice because, well, if I take this point and move it, you see that the points are following. Because this is not a geometric change in the system. This is just a displacement. It's like having an anchor point, a moving anchor point. So there are a bunch of things that you can do with this. Also, I don't know what you are into, but this thing of spatial filling strategies, or this, in this case, planar filling strategy, are processes that are also used in graphic design and this kind of visual applications, right? So you can also say, for example, that this point is moving in time. So for those of you who already know how to create animations or loops in Grasshopper, you can animate this point and have it moving around. So you have this set of circles packed but moving, following this point. So if you don't know how to create loops in Grasshopper, you can take a look at my webinar on loops, which is on my YouTube channel. But anyway, you see that this is actually becoming an attractor. So according to the position of this point, I will have a point cloud concentrating around this attractor point. What if instead of using an attractor point, we want to use a curve? So for example, what if I take a NURBS curve and I select a bunch of points, set multiple points, and create a curve like this, very simple one, like this. And now I want this point during the simulation to be attracted by this line here. In order to do this, it's always the same thing. So I need connection that will be used for the power law component. Okay, so if I have my population of points which come from list A, I must use, for example, a curve closest point, the curve being the curve and the points being list A. So I have this here. And this is also giving me the projected point. So if I connect with a line each point of the population with its projection, I get these lines. And these lines, I can use them as the connection lines. Instead of these lines here, I use them as connection for the power law, like this. And so let me get rid of this preview here. And also, let's reset the simulation. I don't want to look at the points, actually. I just want to watch the circles packing. Actually, I think I did another mistake here. I'm using this as connection, and I'm using also here. There is a problem with the radius, probably. Let me double check what happened. Oh yeah, there is a of course there is some problem here with this connection point. Let me double check. I'm using a NURBS curve. I'm projecting this point onto this curve, and then eventually, instead of using this, the list of points here is being affected and is being used for creating the circles. Okay, so let's see if we use the initial population in order to split the elastic behavior from the. No, we still have these points moving away. I think that this is because my points are actually being part of this power law. So as was happening with this point being not anchored, this is the same stuff. So I still have the anchor point set up like with this. So this is actually what's eventually breaking up this system So if I instead switch between the anchor point and the projected points that I have here, everything should go back to normal. And yes, here we are. And here it comes also the latest one. So this becomes more interesting when we start increasing the amount of points, and also when we better calibrate the region for this populate to a wider area, because this way the circles can distribute along the curve quite better, like this. Now, what's happening in this case is that we have a power law that it's only affecting the circle. Each circle is being basically projected or is going closer to the attractor curve. Okay, but we no longer have a circle packing along the curve. Okay, so when circles are projected in the same area, they do pack somehow, right? But when you have this separation here, there is no reason for these circles to be attracted to each other. Okay, so what we can do in this case is also, let's say, involve the interconnections in the power law attraction. Okay, so for example, we can do two things. Basically, we can convert this line into springs with zero rest length. So these springs will tend to collapse the points together. Or we can involve, for example, the interconnections in the power law. Okay, so we are using now only the connections to the curve, but we could also create, for example, use the interconnections as connections for the power law. Now, in this case, yeah, we have one single list. We must reset the simulation. And you see that now this point tends to move towards the attractor. The problem is that the power law is a barycentrical force. Okay, it always determines what's the barycenter between all the points involved. Okay, so eventually we should use two power laws: one for pulling the circles towards the curve, and one for pulling the circles all together toward each other. So this solution is probably, let's say, less effective. So if I use power law for grouping the circle, packing the circles together, like this one, then I can use another spring, like another spring from line, and saying that I want these lines to have a rest length of 0. So they will tend to collapse totally. So if I do this, you will have another force acting. And so you see that this is what happens. Now, this is extremely powerful, because stiffness for the spring from line is set to 1000. Okay, so if I take a slider here like 5.00, you see that these springs become weaker, and you have the possibility to balance this power law. So power law is more effective when this is higher, and you have this. This is basically setting the springs to become more rigidly zero length, so they work better when this value increase. And so you find the balance between these two values here, which depends on many aspects. Okay, this depends on many aspects, because it depends on what scale you are working at, and well, several other things. So you must find the balance between these two forces, actually. Okay, but you see that they are basically distributing using this attractor as a main rule. And of course, this is another non-destructive edit that you can do, because you can change the position of this point and therefore affect the path of this curve, and you have this power law changing dynamically, and you change the distribution of things. This is good if you want to create some dynamic variation in your design until you find the final aspect for your geometry. Now we are still working in 2 dimensions, okay, but we can easily switch to 3 dimensions. So if I, for example, by the way, this can be circle packing. Circle packing is not on surface, is with circle packing with curve attractor, more radiuses. We can also make this three-dimensional, and actually it's just a natural extension of what we are doing, because the only thing is to create, for example, a populate 3D, or you can use whatever law or whatever rule to distribute points in 3 dimensions. I'm using now a wider box with less points, because now we are going to work with 3-dimensional objects, okay? And therefore the calculation is going to be a little more, well, heavy. So what I want to do is basically the same. So what I need is always the definition of the mutual distances according to variable radiuses. Remember that at any time you can switch back to one single radius by using the same value for all these slides here. Okay, so I copy paste this and use this to create these values. Okay. And also convert all the interconnections in springs. Remember that now the interconnections are 3-dimensional. Okay, so this doesn't mean that the system will not adapt in 3 dimensions. So everything will work perfectly the same. The only thing is that the power law will act in 3 dimensions as well. So we can take, for example, but instead of taking these interconnections here, we can take whatever attractor, but I will stick with the interconnection and the usual negative 5. So it's good value for starting, and bring it here, and also merge these together with a flatten and Kangaroo solver like this. Okay, so if we run the simulation, we see the same behavior but in 3D. And in order to double check, if I change these values, you see that there are some points that are basically moving around. If I increase, you see that the volume, the global volume is increasing. If I decrease these values, you see that the point tend to collapse a little more. Okay, we only have 11 points in this moment, so there are very few possibilities in this packing. And what we can do, let me pause the simulation. After this, as we are not using any other attractor point or any other geometry, the only particles that we get are the 11 points of our simulation. So what I'm going to do, I'm going to create spheres in this case. I do recommend you don't work with the NURB sphere because they are heavier to render in the viewport. So I do recommend you create some mesh sphere. And between the mesh sphere, you have 2 options. There is mesh sphere and mesh sphere X. And yesterday we saw that this is topologically better for some applications. So why not stick with this? And I'm going to create 1 sphere for each particle. And of course, the radius is going to be our list B. Okay, so in this moment, we have a 3-dimensional sphere packing instead of circle packing. We can also do this like in real time, as you can see. And we can also increase, decrease radiuses for this sphere. They still tend to stick together like the circles. Okay, so with this, you can start thinking about filling a volume with some geometries. Okay, we are still not talking about collisions. Okay, so these objects here tends to, let's say, interact together, collapsing towards a barycentric point. Okay, but in a while we will be creating different forces in order to create another type of behavior. And of course, even in this case, you can work with attractors. So if you want to pack these circles using an attractor curve, well, you can use it. You can use the attractor. It's very simple. In this case, it's going to be a 3-dimensional attractor, of course. But anyway, it's more or less the same thing. I'm just going to copy paste and create this curve closest point here. So I'm going to copy it And I'm going to take these points here, and instead of having all flat in the XY plane, I'm going to move them like this. And eventually I'm going back to this area, and also up a little. So I'm creating some kind of three-dimensional path around the position of this sphere. And what I want to do, I want to project my points onto this three-dimensional curve, and I want to create a connection line between the points and their projection. Okay, and eventually I'm going to also increase the amount of points just to have a more interesting interaction. So in this case, for example, I want to use these lines as connection for the power law. So let's reset this. It's yeah, the same thing as before. I'm involving the points for two separate things, and I cannot do this. So I cannot use this connection line as power law. I must use them as as springs. Actually, well, I don't know if it's well. Let's keep things separated. So I just need another springs from line here. So another springs from line. Yes, here it is. And connections, and all the rest is set to rest length is set to 0. Stiffness, eventually, remember that it's a huge value because it tends to simulate exactly well, it tends to adopt exactly the rest length in no time. Okay, this is good for some particular simulation where you want some like specific material to be taken into account, but normally it's not that good. And so you will have the possibility to, well, actually, I think they are collapsing more or less in the same area of the curve because they are all in that region, more or less. But for example, in this case, well, instead of using a populated geometry or populated 3D, if you want to work with an attractor curve like this in 3 dimensions, eventually you might want to use the curve to generate the point cloud. In Heteroptera, there is a component that allows creating, let me see where this is, curve emitter. The curve emitter takes a curve and emit a point cloud from the curve. Now you can see it if we can increase the amount of points. You can see that there is a population of point being emitted from the curve attractor. So if you work with these points, eventually you have already a population of point which corresponds to the shape of your attractor. And so in this case, I would shift to this curve emitter in order to have this distribution of sphere, and then I will just play with them. And now we have to play with the strength of these springs here, and eventually increase it as we did before, so that they become well, actually, oh yeah, the anchor point. I am missing the anchor point, and so the projected point must also be anchor points. But anyway, you can play around with this, and you will have this sphere packing. Well, if I increase this much. Oh, and by the way, I can no longer use the particles, remember? So I must use the list A as geometry and use the geometry for creating the spheres, because else I will be using also the projected point as a generator for our circles, and we don't want that. Okay. So in this case, we must find the balance between the springs and the power law. But these spheres are packing together along the curve, okay, without overlapping. You can use this for creating several structures. For example, now I'm working only with spheres. They simply can't intersect with each other. they can't overlap. So this is one solution, but you can also take this point and the geometry out and use them for some more complex shape generation by using, I don't know, some uh, march, marching cube algorithm like Cocoon or Dendro or whatever you might want to use. So I'm using spheres now, but this could also be a unique blobby shape, taking the shape of the original curve. Okay, instead of using this sphere packing as the final output, you can use the sphere packing in order to compress all the points together and then give them a radius for generating one unique blobby mesh. And one other thing is that when you work with this, remember that one of the options that we already saw in at the very beginning is this multiplication for the rest length and upper cutoff. Because in this case, for example, I'm going to activate this for a while. But remember that if you, well, not this one. Remember that when you do this kind of simulation, the the upper cutoff and rest length can also be higher than the radius that you are using. So you could also have some structure, some three-dimensional structure in the last definition that we saw, where you multiply the rest length upper cutoff by a multiplication factor, and then you keep the object separated, each one with its own radius. Okay, so just so that you know that these definitions are basically well, they can work together, or you can use pieces of one definition to implement parts of another one. Okay, so now let's use this behavior, but instead of, well, I will eventually implement this behavior on this thing because it's not adding some relevant feature to our process. So I will use this to implement a different strategy. So what I want these spheres, for example, to collide with each other or to don't overlap. But I don't want any attraction with a curve. Okay, so I'm not going to use this curve as an attractor. I will just use the curve to create the population of points instead of the populated 3D. Just so that I can distribute this point in a more effective way than randomly in space. So these are the spheres that I want to use. And eventually, well, more than this, I eventually will go into the front viewport and do something like this. Let's move this all these spheres up to a higher level, like here. Okay, so my spheres are being generated like at this height. And what I want now, I want this object to fall down and to start interacting while falling, while, for example, colliding to another object, like a plane. You know? So in order to do this, let's go, and as we are using this kind of method for creating the collisions, you know, we must stick to Kangaroo 099. Okay? So if I go in Kangaroo 099, the only thing that I can do is basically, in order to create this kind of collisions, I can use either collide surface or collide mesh. Normally, I do prefer to work with meshes when I work with Kangaroo, because as it works with meshes, I prefer to keep things consistent by not using surfaces. So in this case, what I want to achieve is that my solid is going to be a box like this one. So quite a big box, and it's going to be like very thin. I don't need it to be exaggerated thick because it's going to be a collision object. And the points that I want to let's say involve in this collision, well, initially let's use the original list of points, okay? And let's see what happens. And also, when you have a collision, this is something that it's quite an important constraint. let's see if it is taken into account properly during the simulation. So we should have already the proper behavior. The problem is that we miss the sorry, let me get rid of the preview of these points. We miss a force that makes this sphere basically fall down. Okay, so we go into forces and take, in Kangaroo 099 it's called unary force. It's not called load. So you must apply this force to your points. So take the least A points. And now there is a vector. That one interesting thing is that in Kangaroo 099 you see actually the vector that is applied to the point, which I find it very interesting and useful, especially when you are viewing the system before the simulation. You know exactly what is going to happen. And the force, therefore, is 0, 0 minus 9.8, which is gravity, actually. I will get rid of the preview and plug this into D4. And also get rid of the preview of the merge. And so this is going to fall down and hit the surface. These points are basically kept together in a very strong way. So it depends on the fact also that the stiffness of these springs is quite important. So what I'm going to do, I'm going to use an 11 slider for the stiffness of this thing. The higher this value, the more these springs will be able to, let's say, fight against the power law. If the power law is strong, then the stiffness must be strong. If the power law is weak, then lower values for our spring are enough for keeping the spheres out of each other. And in this case, you have the possibility for gravity to affect the spheres more and more. So you see that sphere starts to fall, basically. They interact, they collide with each other, but they still fall towards the ground.
Okay, the other option for this multi-object collision, multi-sphere collision, is to have them colliding with an external object, like this one, like a set of little sphere falling inside a ball. This is something that opens a totally new set of possibilities, because what I'm doing right now is I stopped using the power law, so there is no mutual attraction between this sphere, and they just move because of let's say the unary force this time. So it's gravity. Okay, so gravity makes them fall down, and the springs actually start to act only when two spheres start to overlap. Okay, so there is no mutual attraction, there is just gravity. And if by chance two spheres become too close, then the springs just do their job and separate the spheres and have them, let's say, next to each other, but they don't overlap. And the other thing is this collide surface. So I'm using this ball as a collision object, and I am using these points for the collisions. Now, there is no particular, let's say, news in this new script. It's basically identical to the previous one. I just created a vertical box with a populated 3D with all these points in this vertical column, and I made this object, these points, fall down with gravity. Okay. The other thing, I am using here a mesh sphere X, which are this little sphere here, because it's way lighter in terms of rendering the viewport for Grasshopper to use a mesh sphere instead than a NURB sphere. And by the way, there are two types of mesh sphere in the mesh toolbar. In primitive, you will find mesh sphere and mesh sphere X. I do recommend you use the mesh sphere X normally, because it has a more regular topology, because the mesh sphere has poles, north pole and south pole, so all the topology is converging inside this into these two points. So it is a irregular topology, while this one is more extended, let's say. So it's like an inflated cube, as we saw yesterday. So I'm using a mesh sphere X with a low resolution in order to don't stress the computer too much. And I am calculating all the vertices for these spheres, because I want these vertices also to participate in the collision with the ball. Now, it turns out that these points are not taken into account by Kangaroo during the simulation. So if I try to use only the external vertices of these spheres instead, then the center of the sphere, which is, by the way, already connected, because you see this relay is pointing to the list of points. So it turns out that Kangaroo is not taking into account the list of vertices. This normally can happen because of one only situation. And the situation is that these points are actually not part of the simulation. Like they are not considered to be particles. Okay, so if I turn off this and activate Kangaroo, you see that particles out is not taking into account the vertices at all. Now, the only way to bring these particles, these vertices as particles inside Kangaroo would be to go into Kangaroo 099, because we're working with this, and go inside the utility, if I'm not wrong. Yeah, springs from mesh. So basically, what I should do would be to take this mesh sphere X and convert it into a elastic network. Of course, I can do this, and I can program the stiffness of these spheres. 1000 is already a high value for stiffness, so they would be quite rigid. Okay. The problem is that if I do this and I plug also these to the solver, you see that now we see these particles here in particles out. Okay. So this is already set to work, and eventually it might work. The problem is that the simulation in this case become extremely slow. As you can see, it hangs basically. So I'm trying to stop it right now because I don't want to crash the definition. So if you have plenty of time and you want to see these spheres bouncing with their outer surface onto the other surface of the ball, then you must convert these spheres into elastic meshes. Okay, I'm not doing this. I will leave this like it is, because in general it is more convenient to run the simulation as smooth as possible and tweak the geometry, because actually if you perform this kind of simulation, it's because you want to fill this object with spheres. So I'm only considering a very few spheres in this moment. It depends on the populated 3D, only 10 spheres, right? But if you use lots of spheres and you imagine to convert each of them into one elastic mesh, then this simulation is going to run, well, extremely smooth, and eventually Grasshopper might crash, because it's a very time-consuming and process stressing for the computer. So I would recommend eventually that you, I don't know, tweak something like the ball and offset the surface a little, so that when the spheres start to collide like this, you see that they pass through the surface. If you offset this surface a little, then you will have the sphere basically bouncing before touching the real ball, and stay on the inside of this ball. Okay, in order to avoid especially this kind of effect here. So it's a problem of how much stressing is this simulation for the computer.
So if you don't have any additional question, I will switch to another topic, which is basically always like space filling strategies, but with a different type of mechanism. Okay, which is not separate bodies that tend to converge and cover seamlessly a portion or a given surface, but one object that expands and tends to fill the whole area that you give it as a boundary. Okay, so it's a different approach. So in order to do this, we are going to work now. Yes, we are going to work with Kangaroo 2, and we're going to work with collisions. What I want to do, for example, is something like this. Let's take a plane surface. And what I want to do, I want to randomly create a curve inside this surface. So I take 5 points and connect them using a NURBS curve. The only things that I want to avoid is a self-intersecting curve. So I can work with the seed and see when I get a non-self-intersecting curve like this one, then we are good. Okay. Okay, so what I want to do is take this curve and make it grow inside this this region without exiting the boundary. Okay, so first of all, remember that as we're going to work with Kangaroo, of course, we are going to convert this curve into an elastic rope, let's say, and this elastic rope is going to expand in time. Okay, so as we are going to convert this into resorts, or sorry, into springs, then we must convert this this smooth curve into a set of lines or segments. So the easiest way is to rebuild this curve. So if I rebuild this curve using degree 1, what I get is a polyline, and I can determine the resolution of this polyline by tweaking the amount of control points. So if I take an 11 slider, I can increase the amount of control points and therefore get to a better representation of the original NURBS curve. So you see that there is basically no difference between this object and the original NURBS curve. So if I switch between the two, you see that there is no difference. And once we have this, remember that we must convert this into springs, and the component is the length line, and it accepts lines. This is a curve, so I must also explode this object, and this object is being exploded into these small segments, and I want to use these segments as springs. So we already have the springs, and what I want to happen during this simulation is that these springs tend to expand. So I'm going to use, for example, well, length is actually the rest length, so it needs a the final rest length that we want to achieve for these segments. Okay, so if we want to say that the actual rest length is 50% more than the actual length, then we must implement some multiplication here, calculate the length of these segments, and multiply this length by a multiplication factor like between 1 and 2. 1 being exactly the same length as this actual one, and 2 being twice the actual length. Okay, so with this slider, I can program the final rest length between the actual length and double the value of the actual length. So if I take a solver, a toggle, and a button, and plug these springs, and I run the simulation, and I start increasing this value, this object starts to behave elastically. Okay, but there is no no boundaries, no constraint, no self-collision, nothing. So this is like having some elastic body that is completely free to move in space, okay, or in the plane in this situation. So let's start adding some conditions to this simulation, okay? And also let's start to also use the proper method for passing these values to our Kangaroo solver. So first of all, we want this curve to stay inside this this object, this boundary, okay? Because if I do this, you see that the object can come out from the boundary. And the other thing that I want is, for example, that this object cannot self-intersect. So these are the two main boundary conditions that I must define in this simulation. And in the end, what I want to do is actually, well, this is an easy one. I want to see segments. I don't want to see particles or any other thing. So after the simulation, I will take the 3 statistics of this entwine and partition this list using these sizes here. And I'm only interested in the explode tree first branch, which is going to be actually the line. So I can get rid of all this preview and just have an idea of how the line behaves, which is this one. Okay, so everything is ready now. I need only to add the other conditions for my simulation. So first of all, self-collision. How do we implement self-collisions? Well, one way, as we know, is using the sphere collide. Okay, so if I take the vertices of my explode, which are basically the vertices of my polyline, I can define a radius, a self-collision radius. Remember that this radius is measured in document unit. So if it is set to 1, 1 means this distance. And as the segments are very small, it means that they will be basically receive a instantaneous push to bring all these vertices at 1 millimeter of distance between each other. So it's going to be very extreme, this goal. So I'm going to change this to 0.5 and eventually make it act progressively from 0 to another value. So this is going to be, for example, my collision. If I do this and run this, you see that even if I have collision here, the object is not necessarily avoiding self-intersections. Let's do this like this. Well, I have to work with extremely high values in order to obtain non-self-intersecting object. But if the value is not big enough, you see that this is basically not enough for avoiding self-intersection. Eventually, we can also do something like this. We can also make this rope, let's say, expand with a given self-collision radius, okay? Then decrease the self-collision radius, which is still active, and then start to compress the springs once again. So we can also work with smaller values for the sphere collide. But in this case, you see that we must tweak these 2 values at the same time, okay? So we are programming this deformable string here in order to avoid self-collision. Now, this is something that eventually should work, but it gives us some, let's say, uncontrolled situation like this one. So it's normally not enough, okay? So let's see what we can do with another thing, which is always a collision, but it's the collider. So the collider, which is ITESH, is something that you might want to further investigate if you want to create several objects collisions at the same time. It asks for objects and radii. So you see that in this case, you can work several objects, each one with a specific value for the radius. So what I want to program in this collision here is a collision between the parts of our curve. Now, these accept lines or points. We can either work with segments or with vertices, but we cannot work with segments for one reason. If we consider, for example, this polyline, okay, this is the situation. We have 2 adjacent segments like this one. If I say that these 2 lines here are collision objects, and I give them a radius, then what happens with corresponds to the vertices? Because in this case, if this line collides with this one, they cannot be, let's say, constantly in contact. So I cannot do this by assigning this collision object, the collider goal to the segments. I rather use the points. So if I take the vertices and send them to the object, now I have a collision radius, which is going to affect all the vertices of my line. If we work with an a rebuild, and we take a look at the length of these segments, and we take a look at this, you see that if I take a min-max component, you see that minimum we have 0.4071, maximum 4082. So they are more or less identical. So the thing is that we have we also use a average component and see that more or less we have 0.4079. Okay, this is the average value for the length of these segments. So basically, if we know that the length of each segment is 0.4, for example, it means that if we give a collision radius to these points, to these vertices, of 0.2, we are reaching more or less half the length of the segments. And therefore, you will have no, let's say, pushing action determined by this collider. Because if we give this collider a radius which is higher than this distance here, then this point will push the other way, and this point will push the other way. So this will work together with the, let's say, elastic goal in order to expand the segments of the curve. Okay, so this is going to be the action of our collider. Now we can take this average value and divide it by 2, for example, in order to have the initial, let's say, radius, which won't affect, more or less, won't affect the extension of this line, and then take this value here and multiply it by a length factor in this case. So between, for example, 0 and 2, which means we don't want collision basically to be taken into account, like radius of 0, and we want twice the actual result, which means exactly the length of the segments, to become the collision radius. Okay, and then we plug this instead of the sphere collide. Let's reset the simulation. We see that we already have something. Now, if I start to increase this, you see that we start to have an effect when we reach the upper value. Now, when we work with this collider here, this strategy of using a multiplication factor, which is extremely good for determining the rest length of the spring, is not that good for collision object, because the collision radius is better to define it by using a real value. So I want, for example, collision radius to be expressed in units directly. So despite the fact that I have this kind of elastic rope, if I use, for example, a slider like, I don't know, 2.00, and eventually, initially, I leave this to a very low value, you see. When I start to increase it, I have more control over the general behavior. Now, another thing that happens in this case is that the collision radius not only affects two adjacent vertices, but also vertices from different portions of our curve. Okay, so you see that this curve basically cannot even get, parts of this curve cannot even get closer to other parts because of this collision radius. Okay, so this is good because this is more effective than the sphere collide, and this also gives us some control over self-collision and collision between different parts of the same geometry. Okay, so initially I do recommend that you keep this value quite low, because as you have a very important push or expansion push for this object, and then eventually you start to increase the values. And the last thing that we don't want to happen is that this object can, let's say, come out of this square. So this is something that it's easier somehow. There are also some things that are for example, the curve point collide. Keep a set of point outside or inside a given 2D curve. So this is very easy. You can take the vertices, and you can take, for example, the outline of this plane surface. So you can take a wireframe component which gives you the four edges, and then you join curves, and finally you have this rectangle here and use it as the collision object, and interior must be set to true, because else the point will be set kept outside of the curve. So the point will instantly go outside of the boundary. So I'm going to set this to true. And we have the missing goal that we're looking for. And well, this is another collision object. I will mix this with, and you see that already this thing just was pushed inside. Okay, so now this object can no longer escape our square. So if I start increasing the length, this object tends to be larger. Okay, but then I also have the collision, which avoid this object from self-intersecting. And so you see that this object is adapting, it's adapting its shape, and it's filling the space inside this this square, like in a very let's say interesting way. This is an algorithm or a phenomenon which is called reaction diffusion. We are going to program this like with a more let's say high resolution version. Actually, what we must do right now, stop the simulation, go into the rebuild curve command, and instead of using a slider like 100, let's use a 101. So what happens if I increase this very much? So now I have a huge amount of segments, okay? And I am using the multiplication factor in order to determine the expansion factor for these springs. So I will keep this to 1 initially. I don't want this the length of this line to change because of the elastic force. And the collider itself will be a collision, an expanding force. Okay. So if I run this, you see that this thing is already expanding very much because of the collider. Okay. So that's why I told you the collider must be kept very low initially. And also in this case, with this resolution, a radius of, what was the upper limit here? A radius of 10, it's well, just too much. So let's consider, for example, 1, okay, or eventually 2, but not more than that, because of the resolution of our rope. So now we have, you see, this slow expanding curve. It will stop more or less at this point because the push of the collider is already ending right now. But if we start, for example, to increase this value, you see that the self-collision starts to act at a wider distance. Now, if you increase this only the radius of the collider, you already have this kind of behavior. But the best thing you can do is also implement some expansion for the segments themselves, not necessarily the collision, but also the length of the curve can also increase. Okay. Even in this case, if you see that this coefficient is not enough, you can also increase the value, but this depends on the scale of your model. Okay, so it's not necessarily useful to have this, let's say, different range for this slider, but you see that at this scale, with this amount of segments, then it becomes interesting to have a wider range for the slider of the length factor. And so tweaking these values here, you can also create some kind of nice plain filling patterns like this one. Okay, so this is the beginning of this new topic, let's say so. And you see that already tweaking this parameter here, you already have this kind of nice behavior. Tomorrow, what we are going to discuss is further implementation of this reaction diffusion algorithm, and working with one single object, with several objects, and also controlling the shape of the line that we are going to create. Okay. So let me also stop the simulation. Let me reduce the amount of segments. and reset the simulation. So yeah, it can run more smoothly. Remember to always reset the values, because this simulation only works if you start with a proper set of values. Okay, as you get self-intersection. Once you get self-intersection with this object, then it's almost impossible to basically eliminate them. And you see that this thing now works smoothly because of the we have few segments. Well, not few segments. We already have 300, but it's less segments than before. And you can play around with these values and see how this affect the pattern. Okay, but tomorrow we will complete this and we will come up with very interesting shapes. Eventually, you saw also the previews that I've been publishing in last week, mostly. So we are going to get to those results.